I am getting by just fine. It's not like I hate my face. I just, you know what I don't want? I don't want to be like, hey, not only can you see my face here, but now it's 3 times as big up there. I just don't think that's good for anybody. All right, that's my opinion. Anyway, let's get going. So a double displacement reaction. A double displacement reaction. Well, let's start with perhaps an analogy, maybe a tail. You know, so let's say hypothetically that we have, give me a name. That isn't my name.
No.
What do we got?
Charlie.
Charlie. All right, we got Charlie. And Charlie is on a date with, give me a name. Suzanne. That's very heteronormative. I like it. Okay. With Suzanne. So Charlie and Suzanne are on a date. Where do they go on the date?
Disney World.
I'm hearing Chuck E. Cheese. All right. Charlie was like, my name's Chuck. This only makes sense. We're going to Chuck E. Cheese. And immediately, Suzanne is suspicious. She's thinking this guy, this is not going well. But, you know, she's got an open mind. She's, okay, we're having a good time. And at Chuck E. Cheese's, Charlie pays no attention to her because he's really obsessed with skeet ball. And at first, Suzanne thinks like maybe he's trying to win all these tickets so he can like get me a stuffed bear, and that'll be cute. But really, he just uses them to get like pens with superhero erasers or pencils with like superhero erasers. And Suzanne has to admit to herself, she's not having a very good time. She's just, and you know, Charlie is talking about his comic book collection, and he's got a substantial comic book collection, and he's quite proud of it. And Suzanne is less impressed by it. So Suzanne is desperately texting a friend saying, please phone and say there's been a medical emergency so I can leave this place. But her friend isn't answering. So she's scheming. She's coming up with ideas. When they bump into, give me a name. Mark. Okay, there's Mark. And
Jesse.
And Jesse? Okay, is Jesse a boy or a girl?
Could be both.
Could be both. Well, we're going to stick with one, just for simplicity's sake.
The name
oh, no, I know. Okay, so there we have Jesse. And as Charlie and Suzanne are walking around, and Charlie is explaining that Wolverine actually first appeared in the Incredible Hulk comics, and Suzanne is thinking, what if I faked a heart attack? They come upon Mark and Jesse, and Mark is busy describing his love of Say Yes to the Dress. And Jesse is thinking, I would give anything to be watching X-Men cartoons on Netflix right now. And it's like there's this sudden moment of realization as Suzanne is thinking, I love Say Yes to the Dress. And Mark is thinking, this Jessie, she seems so nerdy. And they have a moment where they realize what?
They like each other.
Yeah, they realize this isn't working. This is not constructive. And so, in a completely, you know, appropriate way, and you'll note a metaphor that is entirely wholesome, what happens at the end of this date?
They swap.
Yeah, Charlie realizes that Suzanne wasn't the young lady for him. Oh, he didn't get a sex chain though, so that shouldn't be a skirt. Though it would be okay if he did. So Charlie ends up realizing that his true love, his soulmate is Jesse. Soulmate, yeah. Just you know, if there's a place you're gonna find your soulmate, it's probably Chuck E. Cheese. It's just listen, that's just science. And likewise, at the same time, what does Suzanne realize?
She likes Mark.
Yeah, Suzanne realizes that she and Mark really would be a much better couple. And everybody is so happy with this arrangement, they all decide to go to Harvey's together. Maybe Arby's. Everyone loves Arby's. That's not true. Okay. So there we go. So there we go. That's a double displacement reaction in metaphor. Does that make sense? Now, if I were going to write this in a general form the way we sometimes do, how might I write it? Yeah, I would say like AB, some compound plus another compound yields what? AD plus, and we have to be careful here. Which one should come here? CB. Good. Because we always write metals first and non-metals first, right? So order is going to be maintained. So that's a double displacement reaction. Oh, la-dee-da. Yeah, I forgot to charge my computer last night. Yes?
Can displacement reactions only work for ones with ionic compounds?
Yeah. That's a great question. And to answer it, basically from this point forward in the course, 90% of our time is going to be spent dealing with ionic compounds because the reactions are much simpler. Covalent compounds make complicated reactions. That's, if you take the 4U chem, we will spend a lot of time talking about covalent reactions. But the vast majority of what we do in this course will be covalent or ionic compounds. Great. So I want you to try this one. I want you to have sodium carbonate react with calcium chloride. Take a minute and do that.
I will once I've done my
I'm looking at 126. I don't know. Oh, atomic mass. Atomic mass. Hi. Sorry, I was assuming atomic number. By the way, has anyone else realized that you've got to work out the equations for compounds every time you do one of these questions? Right? So you're going to get so much practice working out formula compounds for the question. It's huge. Tons of practice. These ones too. And on the next page, we're going to talk about how we know it.
You don't want to know how often I do that.
Yeah, that's a great. This has nothing, by the way, this has nothing to do with the activities. And you're going to tell me why.
I'm going to skip on to the next question. That one. No, I mean, my realize it.
That's still CO3. Yeah. And then you have to, so now you have to balance that. So here,
I'm bored.
and sodium takes what charge?
No.
So when you need more, so this has a negative charge. How many? Yeah, and this is negative. But this is positive. So go down here. And then once you've done that, you don't get charged. Now it's back. Over here now. And this is still.
But you still don't know. No, I don't.
That's what you need. Yeah. And how many plugs? No, that would be calcium or plus 1. Calcium is plus 2. Or until the negative 1. So how many of these does it cancel?
Ooh, there's more. Okay, we already said about this one. I don't know here.
So this is plus 2. That's minus 3. Have to cancel.
So then I know.
So chloride.
Your voice is because you're not a great.
Right? The calcium is still got plus 1. So how many do you need to make it work? Right?
Okay.
We should get so your calcium it's got charge plus 1. Always. This is that. Positive 2 is still left with plus 1.
Wow.
So these cancel always. We need another one. That's nice. Sodium recording.
Sodium is why just when it's scoring.
Oh, I have some
Sodium
with
plus
these.
1, chlorine is
They plug in.
A1.
We put the
Calcium is 2 plus.
Oh, yeah.
So that works. So these are good.
Or no.
And now you see the balance. Or we're going to
Yeah, because
see
you
the
don't
balance.
balance that one, you'll
So what do I have to
balance
do?
them on each side.
That's gotta go.
But yeah,
Okay.
that's like
Chlorine is over here.
Two.
Over here.
She has the
No,
beat
no,
people
that's
down.
perfect.
Yeah, 2, right?
2. So they're good. How many C8s?
1.
Good. How many CO3s?
Okay, done.
Just 1. How many CO3s? Good. Good.
Good.
Oh, golly. Let's take a look.
And it didn't do. And it did that. Okay, back to side. Now,
Yeah, like they want to actually know what I'm
and
doing.
all three.
Oh, what replaces what? So this is great. And now you've got a metal with a metal and non-metal with a non-metal. Right? So the metal will have to replace the metal switch parts, right?
But I think that's what
So it'll end up being calcium with carbonate and sodium with chloride. But other than that, yes. This is great. Oh gosh. Okay, and sodium has. Make this -6. So what are they gonna do? So 1 and 2 don't. So this could be 2, 4, 6, 8, 10.
So it looks
They should make 2. How many guys have to make 2? That's right. So it is just the sodium needs a 2.
Okay, so these cancel out.
Does that make sense?
And then you need
Yeah, that's okay. You have them all. And then you see all. They're all right.
green and then
Only one spine size.
So then that's two and zero, yeah.
Only one spine size. Yeah. That's just.
I'm just trying to figure out that.
Now, okay, so
Now,
So I'm pretty sure we have to go to because the VR is negative one and then it's
so you need to balance.
Oh, we also just want to money. Yeah.
Okay, let's try this together. Let's try this together. What is the formula of sodium carbonate? One more to the point, how do I figure it out? Sodium is Na. What charge does it take? +1. Carbonate is what? CO3, and its charge is? Great. So what do we end up getting? Yeah, to make this work, they're going to meet at 2, right? So I've got to double this because 2 positive will cancel 2 negative. So the formula will be Na2 CO3. Good. That's comfortable for everyone? Again, we're going to get lots of practice. What's it reacting with? Calcium chloride. What charge does calcium take? So Ca +2. And chlorine takes what charge? Great. So what do I need here? 2 of these, right? Because then we'll meet at -2 and +2. Okay. And so the formula for this will be what? Great. Before we carry on, is anyone stressed about that? We're good? Okay, now, when they switch partners, what's going to end up with what? This sodium is going to go over and take the place of Ca. They're going to switch. Does that make sense? Maybe I'll... These are going to switch places. Now, does that mean that it will be CaCO3 necessarily and Na2Cl2 necessarily? Or do we still have to figure out the formulas for everything on the other side? That's right. So now we're switching places. So now we still have carbonate over here. But what's the new positive ion here with it? Yeah, carbonate is now with calcium. And what do we need there? Okay, so what's the formula? CaCO3. Good. Yeah, the metal always goes first. Oh, no, it makes no difference. If you had put sodium chloride first, that's just as correct. There's no rule for that. Sorry, I misunderstood, but that's a great question. And what is the next compound? What's the next compound? I know you have it. What's the next compound? Well, what's the positive ion we have left? We have the sodium. What charge does sodium take? +1. And what's the negative ion? Chlorine, and its charge is -1. And so this will give me NaCl. Well, I was going to get there. But since we're being speedy, yeah, why does a 2 here work? You're right, of course.
Even talk the NaCl from the flip side.
Yeah, if we look over on the left, we have 2 sodiums. So I know right away I'm going to need a 2 here. And then in a nice twist of fate, that also gives me 2 chlorines. And on the left, I have 2 chlorines. Then on the left, I still have 1 calcium. On the right, I have 1 calcium. And can I give you a trick? Don't think of carbon and oxygen separately. Just think of carbonate ions. Over here, how many CO3s do I have? Just 1 of them. Over here, how many CO3s do I have? Just 1. Did you guys talk about that last year when you balanced things with radicals? That it's a lot easier just to think of the radical as its own ion rather than balancing carbon individually and oxygen individually. Does that ring a bell? No? Well, we'll get lots of practice now. Okay, I want you to do one more practice. Sodium hydroxide reacts with calcium bromide. Take a minute.
I tried to do the back, but I can't do the back. I don't know what you want. It's impression. I'm trying to find it. And then
It's almost good. Because it's calcium, the oxygen, and chemo. Remember that whenever you have more than one of the lab.
That was your gun study, by the way.
And take a step and cut it off and start with calcium. Yeah, you used it. What's the charge on OH? Minus. And then so that's not. Like this.
like that. No, so yeah, well, calcium has OH is minus. Now let's take a look. Sodium is OH is. So that we say balance it. And if we're not putting number of the OH, we don't need it. We only need the graph if we say the The only thing I'd say, it's fantastic, is once we use the charges to figure things out, they shouldn't be the final. By all means, write them up to help you get the formulas. And then someone who watches this one. What charge does calcium make? OH is -1. So you need how many OHs to make this thing work? And when we're saying we have two of those, we'll different.
I don't have the
Otherwise, what's that? Yeah. Perfect. Good job. Okay, we'll talk about that.
Okay. Sorry, I know I didn't get to everybody, but I also need to finish this class on time. So, sodium hydroxide, what's the formula for that? Well, sodium takes what charge? +1. Hydroxide takes what charge? For this would be NaOH. And all of these reactions, this is something we can know. Every double displacement reaction we do is going to be done dissolved in water. Every single one of them. So sodium hydroxide, and we're going to react this with what? With calcium bromide. What charge does calcium take? Great. And what charge does bromine take? -1. Good. And so what will its formula be? Yeah, CaBr. But then, because bromine only has a charge of -1, and we've got 2 to cancel, it's going to take 2 of them. And again, all these reactions are going to be done dissolved in water. So we start with stuff that's aqueous. That arrow A looks terrible, and B is like completely above what I was doing. Let's try that. Okay, what's going to switch places with what? Jute and a jute. Yeah, so sodium's going to replace what? Yeah, it's going to switch with calcium. And so on the product side, what's my first product? It doesn't make a difference which one you say first, but what did you say first? Na? And what's it now with? What? Yep. And are there any numbers needed for that? No, because Na has a charge of +1 and bromine has a charge of -1. So they're charge balanced already. All right, and what is the other compound? Yep.
Ca(OH)(2).
Very good. And what would that be called?
Calcium hydroxide.
Good, calcium hydroxide. And calcium has a charge of 2+. Since OH has a charge of only -1, it takes 2 OHs to make this thing charge balanced. Okay, good. As I went around, most people either had that exactly or had that with just small tweaks needed, which is good. That's encouraging. Now, the question is this. How do we know that a reaction like this actually happens? All right, here's what we know. If everything is dissolved in water, I want you to picture that. That means that this would look like I was taking a clear liquid and mixing it with a clear liquid. Does that make sense? So everything we start with is dissolved. Now, what will I have to look out for to know if a reaction happens? Color change is possible. other than color change? Yeah, what's that mean?
It means like solid.
So if a solid forms, I'm going to know reactions happen. Does that make sense? So if everything was dissolved to begin with, then I mix them together and a solid forms, that means a reaction. What else could I see that might mean a reaction?
It could be a new odor.
Yeah, and for there to be a new odor, what would have to be released? Gas. And we would, of course, look for what? If we see a gas being released, we would see bubbles. Good. So listen here. The other thing you could possibly see, though not with ionics, don't worry about it. I was going to say you could also see a second liquid form. Like you could see two things that had been mixed together react to form two layered liquids. But that doesn't apply to ionic compounds. Don't worry about it. So we are going to look for a solid to form in the form of a precipitate, or a gas to form, which we'd see bubbles, maybe we'd smell the gas. Does that make sense? So otherwise, if I mix two dissolved things together and all of the products are just dissolved, will I see anything? How would I? Right? I would start with things that are dissolved and end up with things that are dissolved. So if everything is dissolved at the beginning and at the end, has there been a reaction?
Not really.
No. And in fact, when we talk about this a bit more in our third unit, you'll see that when these are dissolved, they pull. The first thing they do is pull apart anyways. So if everything in the product side is dissolved, that means there's been no reaction. There's only a reaction if one of the products is a solid, or if one of the products is a gas. That make sense? So the products have to be solids or gases, which means that the products have to not dissolve in water. Does that make sense? A double displacement reaction can only happen if one or more of the products can't dissolve in water. And you told me that, right? Because you said that I would have to see bubbles, see a gas forming, or I would have to see a precipitate forming, a solid forming. Which means that the only way one of these reactions happens is if something can't be dissolved. Why can I not just use the activity series to know if this happens?
Because it doesn't tell you if they are soluble or not.
Okay, that's part of it, definitely. Why else? I heard you say it. Why is the activity series no good here? Well, let me ask you this. Is sodium higher than calcium on the activity series? Great, so it can kick it out. Wait, is calcium higher than sodium in the activity series? Calcium's higher than sodium? Great, so calcium can kick sodium out, but sodium can't kick calcium out? Do you see how that doesn't work? Does the activity series make any sense when you actually look at this question? No, it can't tell me anything. So we can't use the activity series for this. And I'm going to make a big note of that. Do not use the activity series. We use the activity series to predict if a single displacement reaction will happen. Instead, we have to look at solubility. A reaction will only happen if one of the products is insoluble, if it won't dissolve. So, how do we know that? Hey, another table! And I gave you a really simple one here. You can find more complicated ones that cover more things online. I really like this version. I think it's easy to read. Okay, so let's take a look. So does everyone have this on the second page? Yeah?
The equation with the melons.
We'll go back and balance it after. Or you can balance it yourself. Let's take a look at this. So, I want you to take a look here. Nitrates. Nitrates are soluble. Are they always soluble? Yeah. Any exceptions? No. So if there's a nitrate, it will always be soluble, which means when we put it in water, what letters will go in the brackets next to it? AQ, aqueous, meaning dissolved, right? So any nitrate, calcium nitrate, soluble. Ammonium nitrate, soluble. Magnesium nitrate, soluble. Lead 2 nitrate, soluble. Does that make sense? If I went and grabbed any nitrate from our chemical cabinet back there, I should anticipate that when I mix it with water, it will dissolve. Does that make sense? What about chlorates? Oh, that's a perchlorate, isn't it? ClO4. Though you can put next to it ClO3. Chlorates are, this is true for chlorates as well. Let's take a moment and do that. Chlorates are soluble. They dissolve. Any exceptions? No. But now we get to chlorides. And chlorides are mostly soluble, but there's some exceptions. What are the exceptions?
So when it's with those three elements,
Yep. So if it's with silver, if it's with, what's Hg? Mercury, or if it's with lead. Does that make sense? Iodides, same exceptions. Does that make sense? Sulfates. What are the exceptions for sulfates? Sulfates are mostly soluble unless they're with what? Yep, and I think it keeps going. Good. So I want to go back to this previous question. And we want to see if this reaction actually happens or not. So we have to look at both of the products. All right. So let's look at the first product, which is what? Sodium bromide. So let's look that up on this table. Is there any way looking at this table for me to know if sodium bromide is soluble or not? Yeah? Yeah, if we look at the bottom, it tells us about some of the positive compounds. Does that make sense? And we see that sodium is always soluble. It will always dissolve in water. Does that make sense? If something has sodium in it, it will dissolve. So how do I say that here? How do I show that since this has sodium, it will dissolve? Yeah.
I have a quick question.
Yeah.
Say that you had like Na and SO4. Does it matter if both are soluble or both are insoluble?
This is a guide that looks at both ions. But if you look, you see here where it says like carbonates aren't soluble? The only exception is group 1, which includes sodium. Does that make sense? So it's not like one of the ions is soluble or not. This whole thing, sodium bromine, either dissolves or won't. But we can look for hints in the positively charged ion or the negatively charged ion. Does that make sense? So just work your way down the chart. Does the chart that I gave you say anything about bromine? No, so we can't use that as a hint. Does that make sense? But it does tell us something about sodium. So, did that answer make sense, Alondra? Did that help?
Yeah.
Yeah? Good. So how would I say that this does dissolve? Yep, how? Very good. That's right. AQ. Now, so far, all our products are dissolved. Do I have a reaction yet? Because what signs are we looking for a reaction? We either have to see a participation. We either have to see a precipitate, which is a solid forming. What would that look like? It would get cloudy. Stuff would start to settle to the bottom. So we either have to get a solid or we have to get a gas. But this dissolves. Is that a solid or a gas? No. So far, no reaction. Let's look at the next one, calcium hydroxide. Let's go to the table and see if this tells us anything about calcium or hydroxide. Do I see calcium down here? No, so calcium's not going to help me. Oh, but I see hydroxide. And hydroxide should be insoluble. Unless it's with calcium. Oh, so this one's going to be soluble. Right? Which means that I am going to have to put an AQ here. And now, does this reaction happen? No, no reaction. This is no reaction because both products dissolve. Does that make sense? So this one did not react because both of the products dissolved. With that in mind, I want to try these next two examples. I want you to try them. So listen, you have to do the reaction no matter what. Does that make sense? Because you have to see what the products are. And then once you've done the reaction, and by the way I'm going to show that this doesn't react is I'm going to put a big old X through that arrow, showing that, like, hey, that does not react. By the way, this table, I'm not pretending that this table has everything on it. So you could potentially get a lab question or a homework question or an assignment question that goes outside of this, and you will have to Google if it says like strontium permanganate. You might have to Google, is strontium permanganate soluble? That's okay. But on a test, everything will fit this chart. Does that make sense? So I won't give you something on a test that you can't figure out with this chart. But be in mind that this chart, I picked one that was small, so it didn't take up 52 pages, but it doesn't tell you everything. Does that make sense? Okay. So I want you to try the next two reactions and see what you get. Yeah, of course. Oh, I'm coming right up. Guys, can we discuss something that I feel like I've already mentioned like 8 times? I don't need to know about your bodily functions. If you need to drink, if you go to the bathroom, if you feel like vomiting, if you, or just whatever, like just whatever, your personal little, little, that sounds dismissive, whatever your physiological needs are, I'd like you to use them. Okay? I think that's a reasonable policy. And don't use the privilege, and we won't have to talk about it. Yes? Oh, that's a good question. Let's use sch3u4c, just so we're all on the same page. Yeah, for the sake of this, you're a step ahead, that's great, but let's just all do 2+. Let's make it live. Yeah, we can do that.
Your code for you to try to solve.
I like it, but first, get to work.
Ooh, I found this lightning chart.
I wonder if I have, to make your life easier.
No, I found a nitrate chart.
You found what?
A nitrate chart.
Good. I encourage you to use it.
You like Wikipedia?
Yeah, sure. I like Wikipedia just fine.
Oh, there's reviews.
Does anyone have, from various times I've handed them out, 2 copies of the periodic table of the ions, by chance? Anyone have a double copy of that? Oh, good. Then we snag the one from the test and kept it.
I think we all have one from the,
Yeah, that's really second. Thank you. Ellen, you may find this helpful, just for simplicity's sake. Justify ionic charges. If this for doing these kinds of questions, it's a lot
which
more.
month is it?
Use the 2+.
So I'm doing both.
That's okay. I mean, listen, more practice isn't going to hurt you.
I can't find
Yeah, of course.
anything. This type doesn't even tell you what the nitrate reactions or anything. So I can't even find it out.
Okay, so this one comes in and this one is the.
So I didn't bother balancing that reaction, by the way. Now, do you see why I didn't bother balancing that reaction? Because it doesn't happen.
That's so easy. Gotta practice
Oh, I
balancing.
disagree. But I mean, nothing wrong with practicing balancing.
I can't find it. It's still in though.
Yeah.
I can't find whether or not nitrate or nitrate.
Oh, sure you can. Nitrates are
Yeah.
soluble. Are there any exceptions?
I don't.
By the way, I'm not going to give you any difficulties in the question. Everything in the question is going to be solvable. Okay, so you don't have to look those up. You can for practice, but
So none of the reactions happen.
For the second
I think this one happens.
or the fourth example.
But no,
Yeah,
no, it doesn't.
use the 2+.
It doesn't. No.
Let's take a look. So you're going to end up with mercury chloride, right?
None of these are so
Chloride.
like insults.
Really?
No.
Make the products. You have to make the products first. You can't do anything until you made the products. Yeah. Okay, well, first do the reaction, and we'll talk about the reaction. Okay, so let's, guys, would it help if we did this one together? Seems we have 6 minutes left. Let's do this one together. Okay, so we have mercury nitrate, and we're going to use the 2+ ion. So mercury has a charge of 2+. Nitrate is NO3. What's its charge? -1. Good. So how do I make this work? What's its formula? Good. We need 2 of those to make this thing work. Okay. And that dissolves in water. A, because I gave it to you in the question, so it's got to dissolve. But B, if you look, all nitrates are soluble. No exceptions. Okay. And this is reacting with? This is reacting with? Are we at the point where I can just put this down? We've been seeing a lot of sodium chloride in our chemistry lives. And obviously, we just know from personal experience, table salt dissolves in water. So everything we start with dissolves, which we expect. What's going to switch places with what? Yeah, these are going to switch. By the way, this is not something you have to draw. I'm just drawing it for our purposes. So our new first compound will be what? It will be what? Sodium nitrate? Sure. So sodium takes what charge? +1. Nitrate takes what charge? -1. So what will the formula of this be? Very good. That's right. NaNO3. Right? No need to add any numbers. It's already charge balanced. And that leaves us with mercury reacting or ending up with what? Hg2+ is going to end up with chlorine. And what charge does chlorine take? So how do I need to do this to make this work? Good. We're going to need 2 of these. When it's on its own, yes, but it's not on its own here. It's in a compound. So diatomic only applies to when it's by itself. Okay, so what will the formula for this be? HgCl2. Good. Now we have to look these up. So let's talk about this thing. Which one do you want to look up first? Sodium nitrate or mercury chloride? Okay, let's take a look. We're going to look for chlorides. So let's look down the left. And we're looking either for mercury or chlorine in this list on the left. Do we find mercury or chlorine? Okay, we find chlorine. What is the rule for anything with chlorine? Except what? Oh, so one of the exceptions is mercury. So this is going to make it soluble or not soluble? Not soluble. And the word for that is insoluble, of course. But I sometimes say not soluble just so we can hear it more directly. So if it's not soluble, what's it going to make? A solid. Does that make sense? If it won't dissolve, it's going to make a solid. Great. What about sodium nitrate?
Will chlorine still be soluble if it was mercury +3?
I don't know. I don't know if that's one of the exceptions. It looks like it's not from there. So it looks like if we use the mercury 3 ion, we would not get a reaction. Now, what about sodium nitrate? Let's look at this table. Do we find sodium or nitrate on this list? I think we find them both, actually, and I think they tell us the same thing. We find sodium there, and we find nitrate there, and it doesn't make a difference because they both tell us what? Yeah, it is soluble. So what am I going to write next to sodium nitrate? Okay, but did a reaction happen here? You betcha. And how do you know? Yeah, this is a solid precipitate. And that means this is a reaction. Precipitate. So this reaction does happen. Does that make sense? So you always have to find a product that won't dissolve for a reaction to actually happen. And if you can't, you just put an X through the arrow. You say this reaction doesn't happen. By the way, is this thing balanced? No, it's not, is it?
No, put a 2 for the Na and a 2.
Okay, now we're closer. Where else do I need a 2 now? Yeah, and now we're good? Cool. Yeah. Please.
I've noticed that in the table where it says
Yep.
does that mean then that technically mercury is diatomic as well?
When you see that, mercury sometimes makes a diatomic ion, which for the purpose of this course, you don't need to worry about. But as you get further in chemistry, mercury is not diatomic when it's on its own, but sometimes when it makes an ion, it is actually diatomic, which is beyond the scope of this course. Is that a fair answer? Okay. I've got some homework here for practice for you. Grab it on the way out. Make sure you do it. It's important. I would love to. Would you like one as well? Yeah, please do.
I was having a little trouble going.
Homework! Homework!
Try to leave. That would be.
This says your textbook, obviously, I'm giving you the textbook again, so.
I don't think I'm
Yeah, I am actually.
my back hurts.
I wonder why don't you just like put something in your backpack instead of or in your locker?
The first time I ever did it a few years ago, I was like, oh, this is delightful. I feel like a kindergarten teacher. And you know, the first time I taught it, we made a song, and that was fun. But there's something about the just chanting it. I really like it. Yeah, exactly. It feels more like a punishment, doesn't it?
Yes. And Mr. Linda, do you want me to put this somewhere? Or?
Yes, just make a pile on my desk.
Okay.
I decided that in my teachables, it's going to be physics, and chemistry.
So that is just teachable spread.
I know. Leaving out biology because it's just not for me. But
Well, the other thing with bio is every gym teacher in the friggin' DSPN has a bio teacher.
I know. So
So you never get to teach it. I love biology. I've taught biology like twice in my 10 years.
yeah, I'm not a huge fan of biology. You know, it's interesting. It's just not for me.
Well, then, yeah, you definitely don't want to teach it. Guys, how you doing? Come on, guys, how you doing? I'm well, thank you. Look at you, what is this?
Because I did it for
Perfect, thank you.
I completely forgot it.
Are you